So today we are going to review sampling distribution and central limit theorem. Okay, so we'll talk about what sampling distributions are and how it connects to the central limit theorem. So sampling distribution is a probability distribution of statistics that is obtained through repeated sampling of a specific population. It describes a range of possible outcomes for a statistic, such as the mean or mode of some variable of a population. So let me copy this definition and see what it means, okay? Um, so let me do this. So, imagine you have some population. So let me do this. So an example of this would be um, something like this. Okay, so let's say the population is people at College Station. Okay. Now, what you're interested in this is, let me do the variable is the height. The parameter is the mean or the average height. So let me define this situation, okay, where your population is some population, some people at some city, let's say College Station, and your variable could be anything. I'm doing height here, and your parameter is the average height, right? So the parameter is often this is unknown, and we use sampling to get the statistics to have some idea about the parameter, right? So try to read the definition and see what I'm saying, okay? So the population, what you do is a sampling distribution is a probability distribution of a statistics that is obtained through repeated sampling from a specific population. So imagine you are sampling, let's say 100 people, you have one sample of 100 people, okay? You have another sample of 100 people. So you have a bunch of samples like this. 1, 2, and many. So from each of these samples, what you can do is you can get a statistics, right? Your statistics is the mean height. So you can get x1 bar, x2 bar, and so on. And the distribution of these statistics is called the sampling distribution. Okay, so the distribution is called the sampling distribution. Your x1 bar, so let me just give an example. Your x1 bar could be could be 5.5. The second sample could have an average of 5.6. The third sample could have an average of 5.5 again. The fourth sample could have an average of 5.6, let's say. And the fifth sample could have an average of 5.5 again, 5.4. Um, just just an example to help you guys visualize this, okay? Could be 5.4. Let's say these are your, so there are 8 different samples of the same size. Each sample is 100 many people. And what you're getting, what this is your statistics, right? This is your average height for the sample. So what will the histogram of this look like? It'll be, like 5.5, 5.4, and 5.6, something like this, right? So this is called your sampling distribution, okay? This is what it means when you say a sampling distribution. You take multiple samples, you take repeated samples. So if you look at the definition again, oops, sorry. So if you look at the definition again, a sampling distribution is a probability distribution, is this distribution of a statistic. So a statistic could be your mean, it could be a proportion. So in this case, our statistic is the mean, right? Of any statistics that is obtained through repeated sampling from a specific population. So that is what exactly we're doing. We have a population, we repeatedly sampled people from that population. We calculated the statistics and we plotted its distribution, okay? And that is called the sampling distribution. Any question about this? No? Is this clear? Yeah? Okay. Now, the thing is, what about n, right? So how does thing change when you change your number of subjects? If instead of 100 people, I did 200 people, then something will change, okay? So you have to be, the number of people you sample plays a role in the sampling distribution. And the idea is that the more number of people you sample, this distribution will go to a normal distribution, okay? What I mean by this is this, okay? So you can look at this picture. When you only sample 2 people repeatedly and calculate the average and plot its distribution, you see that it's not so much normal, right? It's going all over the place. You increase the sample size to 3, and then you see that it's becoming a sort of a normal distribution. You increase the sample to 4, more normal. So the more samples, the more n you have, the more people you sample repeatedly, the more normal the sampling distribution becomes, okay? So that is one thing you have to know, okay? So now let me talk about what the central limit theorem says. So the central limit theorem says, so that is what the central limit theorem says, okay? As n increases, your sampling distribution goes to a normal distribution. So as there are different definitions. The most simple one is, to understand as n increases, the sampling distribution will go towards the normal distribution. With the mean, so with the mean equals to mu, this mean is the population standard deviation, population mean, sorry, and the standard deviation is sigma over square root of n, where sigma is the population standard deviation. Okay. What I mean by this is the x1 bar, x2 bar, x3 bar, and so on that you collect from different samples. When you plot its histogram, when you plot its distribution, it's gonna be a normal distribution. It's gonna be a normal distribution with the mean center at mu and a standard deviation of square root of sigma over n. Okay. So x bar follows a normal distribution with mean mu and this. Okay, where the mean is the population mean, and the standard deviation is the population standard deviation. So coming back to the original question, right? So coming back to this, okay, what's happening here? We are interested in the mean height of the population, which we don't know. We took a bunch of samples and we plotted its sampling distribution. Now the center of this sample, the mean of this distribution is gonna be the population mean, okay? That's what the central limit theorem says. This mean of x bar is going to be the mean of the population. Let me draw another slide to make it clear. So on the population side, what you have is your x, your random variable is the height of people at A&M, right? This is your random variable. And what you want to find here is this, is the mean height. What is the average height? What is the average height of the people at A&M? Now you don't know, this is unknown. The mean height, let me say this is mu, and this is unknown. Okay. So how do I find this? I use central limit theorem, right? I take many samples from the population. Let's say n is 100 again. I take one sample, I find the sample mean of that sample. Okay. I take another sample of same size, and I do this many times. Let's say I do this 100 times, and I plot the distribution of this guy, of this guy, and the center of this distribution is going to be your parameter. Okay. Does that make sense? Any questions? Is it confusing? Okay. So there are two important things, okay? What is a sampling distribution? So first, I mean, just a revision on distribution. Distribution means, for any random variable, there could be different possibilities. So distribution gives you an idea of how the probabilities are, right? So let me do it again. So these are all the different possibilities, different possible values. And this is sort of the probability density, the different, the probabilities you can think. This is what it means when I say a distribution, okay? A distribution, if a normal distribution means that these set of possible values that you might have has this sort of probability. The probability in the middle being the highest, and as you go away from the center, the probability decreases, right? So this is one distribution. Another distribution could be, so this is a normal distribution. Another distribution could be, a uniform distribution, where the probability, so these are all the possible values, where the probability is not changing. For every possible value has the same probability. Okay, so this is a uniform This is a uniform distribution. So this is what it means when I say distribution, okay? You have a random variable. You have a random variable that can take different possible values, and you sort of see what sort of probability they have, what sort of probability each possible value have. Okay, that is what distribution tells you. And the same goes for here. Okay, so these are the different possible values of. So what are these? Can somebody tell me? What are these on the x-axis? When I say a sampling distribution, what are these on the x-axis? Sorry? For the height, or how am I doing the sampling distribution? Is the different possible values of the average height of each sample, okay? So look how I'm doing. This is x1 bar, x2 bar. So whenever you take a sample and calculate the sample average, it could be any value, right? So x bar is the sample average random variable. Okay. What do I mean by a random variable is that it can take different values. You take one sample of 100 people from College Station, asks for their average height. It will be different from another sample, right? So the average is changing as you take different samples. So you can represent it as a random variable, and this is your x bar, okay? These are the different possible values that you can get when you take a sample and take its average. So these are the different possible values of sample averages. And the distribution, you have the probability density, or probability. So what will be the probability of these possible values? Okay. It could be this. It could be a normal distribution. So it could be any distribution. Okay, let me say it's a distribution like this. Okay. It means that this guy has a high probability. This guy also has a pretty high probability. So this is also your sampling distribution, right? Sampling distribution, in very simple words, is how are the possible values of a sample average distributed, okay? How is it distributed? So that is what the sampling distribution tells you. Now comes the central limit theorem. Central limit theorem kicks in when you have a large enough sample, okay? When you're taking large enough sample, then this sampling distribution won't be any random shape. It will be a normal shape. That is what central limit theorem tells you. So if you take samples of size, like let's say 5, okay? If sample is 5 and you take a bunch of samples and calculate the average, then your x bar could be any shape, okay? But as n increases, and you take a bunch of samples, now the sampling distribution will be normal. It won't have any other shape than a normal distribution. where the center is the same as the population mean, and the standard deviation is square root of n. So x bar follows a normal distribution with mean, mu, and does this make sense? Yeah. Okay. So first thing, sampling distribution is completely sampling distribution means the distribution of your sample averages. Okay, it can be any distribution, but if you have a large enough sample, central limit theorem says that the distribution shape will be a normal distribution. So you can see here too, right? So as n is increasing, it's going to be more normal distribution. Yes. Okay. Yes. Yes. Yeah. So this is only when your where did it go? Yeah. Where your x bar. So let me. So in a binomial distribution, your x, your random variable, could only take two values, okay, 0 or 1. Okay, then you can fit a binomial distribution, but here x can take any value. So it's a continuous, it's for a continuous case, like height or weight, height or weight could be any possible value, right? So yeah, you're right. So when x is continuous, okay. So so I don't, yeah, this is not that important for now. You can skip this. Um, let's come to the central limit theorem. So this is what the central limit theorem says. Okay, so try to read this once and try to make a sense of it. The central limit theorem states that if you have some population with some mean, okay, some mean mu, and some standard deviation sigma, you don't know what mean mu is, you don't know what standard deviation sigma, you don't know what this is, you don't know what this is. But imagine, you can imagine the example I gave, right? Where your population is the college station, your mean is the average height, and the standard deviation is the standard deviation of those heights. So if you have such case and you take a sufficiently large random samples from the population with replacement, then the distribution of the sample means, this is called the sampling distribution, will be approximately normally distributed. Okay. So so imagine this is your all the different values of height. So imagine the x represents height here with some population mean mu and some sigma, and you take a bunch of samples, and this sampling distribution x bar will be a normal distribution, okay, centered at mu with a standard deviation of sigma over square root of n. So that is what the central limit theorem tells you. And even the use case is that even if you don't know mu and sigma beforehand, you will know what mu and sigma is after you use CLT, right? When you have this distribution with you, you'll see what the center of this distribution is, and that will be the population mean. You'll see what the standard deviation is, and sigma over square root of n is, let's say, 0.5, then you can find sigma from here, right? Yeah, it is similar. Central limit theorem and law of large numbers are connected. When n is large enough, your distribution goes to some specific distribution that's a Gaussian, that's a normal distribution. So Gaussian, normal, same name, okay? And you can see here too, right? When I take a bunch of samples of 10,000 people and plot its distribution, plot its histogram, you see that it is a normal distribution, but not a perfect normal distribution, right? And then as you see, I increase the sample size. I think it's supposed to be 2,500, 1,000, 2,500, 5,000, 10,000, 25,000, 50,000. Absolutely normal, right? So as n is increasing, you see that central limit theorem is kicking in, right? The sampling distribution is becoming more normal and normal. And this 4.0 is your mean. So let me see if I can zoom in. This 4.0 is your mean, right? And whatever the standard deviation of this distribution is, oops, whatever sigma over square root of n is, let's say 0.5, then you can find the sigma for your population. Okay, so even if you don't know what the mean and the standard deviation of your population is, you can use central limit theorem. You can take large enough samples. You can use this sampling distribution and see and find out the unknown things in your population. Okay. Does that make sense? Any questions? Any questions on this? Okay. So this is largely the idea of uh, central limit theorem. Now there's some like some other cases that I want to discuss, and I think when n, so the question is, how many samples do you need for the central limit theorem to work, right? And um, a widely used number is 30. If you take samples more than 30, then the central limit theorem will start to hold. Okay, so n is greater than 30 is a good lower bound. The more samples you have, the better. But what about the minimum? Okay, if somebody asks you, then it'll be 30. 30 will be the minimum people you need. Okay, so this is sort of the minimum requirement. So let me ask you a question. Okay, so imagine any population again. So people in Asia, Asian people or whatever, um, people in Asia will be people in Asia. Okay, is your population. Your parameter, let's say average weight. And what is your variable? If the parameter is the average weight, what is the variable? Not the height. If my parameter is average weight, what is my variable? Weight, right? Yeah, no, you're good. So variable is weight. So your random variable, x, is also the weight of people in Asia, right? Your random variable always associates with the variable, okay? Because this can take any values. So what you are interested here is is what is the shape of this x? Okay, what is the shape of this x? Something like this. And what is the mean? What is the mean? And what is the standard deviation of this variable? The mean is the parameter, and the standard deviation tells you about the spread. Okay. Does that make sense? So this is making sense to you guys, right? So this is what we want to find in any sort of statistical question is you have some population, you have some variable of interest, weight, then you define a random variable so that you can do some mathematics, so you can do some statistics with it, where the random variable represents the weight, and you want to see how is the weight of the people distributed, right? Which you don't have any idea about. So you don't know the shape of this, you don't know anything about this. So what you do is you take multiple samples. Let's say I take sample of 40, sample size of 40. And what about my sampling distribution? So it'll look like a normal distribution, right? And let's say the mean is 120 and the standard deviation is, so this is the mean and the standard deviation is 0.4. Okay. Now so based on this, can you go back and tell me what the mean and the standard deviation of your population is? From the sampling distribution. So this side, the left side, you don't know anything, right? We just want to see what shape or what the mean is and what the standard deviation is. The mean is the parameter. The standard deviation tells you about the spread. Now, what do you guys think? It will be, yeah, but not exactly, okay? So the mean is the same. This mean is 120, but the standard deviation is different, okay? The standard deviation is sigma over square root of n. This is what the central limit theorem tells you. So how do you solve for, if the standard deviation of this distribution is 0.4, what is the standard deviation of the population distribution? What is n here? 40, right? And whatever you get is the standard deviation of this guy, of the population that we had no idea about. So this is how you use central limit theorem. Does that make sense? You use the central limit theorem, you see where the mean is, you see what the standard deviation is, and you can trace it back to your population, okay? Any questions? Now, another thing is, you don't always need n greater than 30, okay? When you don't know the shape of your population, then you need n greater than 30. But if somehow you already knew that x was a normally shaped distribution, okay? Your population, your weight, was normal shaped. Your x is a normal with some mean and some standard deviation. Let's say you knew this. You want to find the mean, you want to find the average weight, you want to find the standard deviation, you want to find the spread. Then, when you take a bunch of samples, x1 bar, x2 bar, and so on, and draw the sampling distribution for x bar, it will be a normal distribution even if this is 5, okay? So So I know I might have confused you guys. So central limit theorem is, so there are two cases. Do you know the shape of your population distribution or not? If you don't, then you need, for this to be, for your sampling distribution to be normal, you need at least greater than 30 sample. Okay, if you don't have any clue about what the shape of your X is, then you need large N greater than 30 so that central limit theorem kicks in so that you know that X bar will have a normal distribution. Okay, so that's one case. Second case could be you might know that your weight of people in Asia is normally distributed, but you might not know what the center of this distribution is, and you might not know what the spread of this distribution is. Okay, in such cases where you know the population distribution, you don't need, there's no restriction on the sample size. Okay, you don't need to use central limit theorem. This will be a normal distribution no matter what, no matter how large of a sample you take. So this X bar will be a normal distribution with this. So I know it's confusing at first, but it's not really that bad. Okay, you always you always have a population, you always have a variable, you always have a parameter that you want to know, and then you take samples. You use the sampling distribution shape. You exploit the fact that this shape of the X bar is going to be a normal distribution. Um, if you know if you don't know X, then you need central limit theorem to dictate the shape to be normal shaped. So you need your sample size to be greater than 30. If you know the shape of your population, then you don't need central limit theorem. You can just you'll know that X bar is going to be a normal distribution anyways. Okay. So there are like a few sort of things you have to be careful. What is the size of N? Do you know the shape of your population distribution or not? And stuff like that, okay? Yeah, so that is all I have for sampling distribution and central limit theorems. If you guys have any questions, happy to answer. And if you guys want to discuss anything else, let me know too.